Okay, yes, that's me. If you want to check that out, that's all I have. And this is about WebAssembly. So who many has at least some idea what WebAssembly is? More than half, maybe. Okay, that's good to know. So if we go to the WebAssembly website, they say this. WebAssembly is a binary instruction format for a stack-based virtual machine, which is true, and also would be the same description for Java, I guess. Then it also says Wasm, as it's abbreviated, is designed as a portable compilation target for programming languages enabling deployment on the web for client and server applications, which is less true these days, so maybe they should update that part. Wikipedia says something similar, a bit more verbose. It defines a portable binary code format. That's true. And a corresponding text format. Yes, it's true. I don't know if it's necessary to include in the definition. For executable programs, as well as software interfaces for facilitating communication between such programs and their host environment. It's a bit more correct, but still pretty wordy. So what it actually is then is just a way to take a language, usually C or C++, and you compile it into a WASM file, and then you run it in a runtime. And the runtime has traditionally been just a web browser. This sounds a bit like Java, which was something we used to run in the web, but this is, of course, it comes from it has a different background, which I will get into now, actually. So, some history. Well, the history, I guess, really starts with Java, but I'm going to start in 2011 when Google released something called Native Client. So this was a way to run executable code like x86 and even ARM directly in the browser for performance reasons and such. And they used it for Google Earth initially, I think, but it was a bit, convoluted, and they wanted other vendors to use their standard, but I think Mozilla thought that was maybe not the best idea. Instead, this guy at Mozilla called Alan Sakai, he thought, why don't we just compile C++ directly to JavaScript? So he wrote an LLVM backend that did just this and released it, and it was called mscripten. And this was the first kind of tool chain to do this. It's still around. It's still one of the big ones. And it worked fairly well. You could take any kind of C program and run it with decent speed in the browser. But as he wrote his backend and the code that he produced, he realized that he only needed a very small subset of JavaScript. I can actually show you. Let's see if you can. I'm going to jump into another. This is from another slide. I don't know if it's okay to. But this is basically the C code and then the actual JavaScript code that was generated. We can take something a bit more advanced. So what you can see is that basically he just used one big buffer for the entire heap. And if you want to address floats, you just have like a view into that buffer. And then, so the only thing you need is like one huge array of memory, and then you do operations on that memory. So it's not a lot of JavaScript needed here. So he realized that by removing all those checks or that dynamic behavior, you could actually get it even faster. And they define this as, let's see, where is my mouse pointer? It's there. ASM.js. And this subset, now we were looking at speeds of like just a 2x slowdown compared to native code. So that was well good enough for a lot of applications already. And at this point, I think that Google kind of realized that this might be a better way to go, especially since it was kind of an easy buy-in. I mean, Mozilla just said that here's the tool chain that you can use to compile and run C++ code. It works in any browser, but it's faster in ours. So it was kind of a given that they would just optimize their own JavaScript runtimes to support this. But still, JavaScript as a sort of a container for this code, when JavaScript was not really what you wanted, was maybe not the best idea. It was a good first step, but then so they came to the conclusion that yes, we need a better format than JavaScript for this. Something that's smaller and easier to parse and verify that it's correct and that it's separate from JavaScript. And this is where we come to WebAssembly. And this was now was initiated by Mozilla, and mostly Mozilla guys, but still Google and Microsoft was in on it now. And now we have a standard and we have a specification, and things start to take time, as it always does when things get big like this. But still, it has been steadily developing since then, I guess, and used in a lot of places on the web. But something happened a few years later, something called Wasm, or I don't know how you pronounce it. But basically, they added, or this is an optional set of functions that you could add to your runtime to get access to things like sockets, file opening, reading, random numbers, etc. So now we have the ability to actually run WebAssembly outside of the browser. Because before, you could, when you run in the browser, you had access to all the APIs that JavaScript had access to, which was that you could access the DOM, you could use WebGL to render stuff. But that was only for the browser, so it was kind of not as useful to run outside. But now suddenly you could. And then this is what led to in the WebAssembly being used in other domains. So it used to be only browsers. But now, after this, we kind of get two more use cases for WebAssembly. And the second there is server side is pretty interesting, but I'm not going to talk about it because I don't know how it works, more than to say then for microservices, it kind of makes sense. You can allow people to use any language and compile something that is pretty safe to run. So as a replacement for Docker, I think it seems to make a lot of sense. But in my day job, I'm mostly concerned with using it in embedded environments, and also that allows me to sort of look a bit deeper into how WebAssembly works, because it's like how the memory is accessed and how code is run is more important when you're on a limited platform. So we get into runtimes. So yes, this is how it used to look. You only had C++, you only had the browser, and you had this Wasm file, which was the sort of the executable. But now we have a lot more languages and a lot more runtimes. So, by the way, if you have a question, don't feel free to ask when it comes up. So we still have the browsers, of course. And we have a bunch of new runtimes. We are using the second there that's called WAMR, I guess, which stands for WebAssembly Micro Runtime, which is focused on embedded development. So it's supposed to be not use as much memory and work on real-time OSs and stuff. And then you have the two to the right there, which are both in Rust and kind of similar. I think they target mostly the server-side things. And then we have Wasm 3, which is a nice kind of, I think it's leaner as well. It works, it's supposed to work on embedded stuff. And the languages, there's a lot of languages now that has some kind of support for WebAssembly, but few of them has like mature support. So it's a bit tricky still. C and C++ is still like the language to use. WebAssembly comes from this idea that it was for C and C++. It was based on this model. You have a heap, and you have things operating on the heap, and it didn't fit as well with other languages. But still, most languages have some kind of support now. Rust has very good support, I've seen. AssemblyScript is a language. It's what we're using now. It's actually only targets WebAssembly. It looks like TypeScript, but it's much more limited. It's like a subset of TypeScript. But it produces pretty small code, but it's kind of limited. But it works for us, at least. So now we're going to get a bit more technical, I think. Yes, let's start with the Wasm files, which are like the basic components of this. It's not a magical thing. This is kind of a pointless diagram, but it has a header and a bunch of sections. And the sections are things like this. We're mostly going to deal with the function code, or maybe a bit about the data section, but it's the code that we are interested in here. But I think the specification says that you have to provide them in this or a specific order, because they want you to be able to stream them over the network quickly. Okay, now we get into the code. So a few things about WebAssembly before we start looking at actual opcodes. It's stack-based, just like the JVM. That means you don't use registers. All opcodes operate on a stack. So to do anything, you have to push values on the stack and get values back from the stack, which is simple to sort of design around, but it's maybe not super fast. Then to store variables and stuff that you use in your code, you use something called locals. But again, you cannot use these locals directly. So to read a local, you need to first put it on the stack, and to store it, you need to read it back from the stack. And then they have a pretty interesting way of dealing with control flow, which we will get back to. But it's one of the better inventions, I would say, for the whole how the opcodes work. So at this point, I think we should we'll start with just to get an overview. I'm going to show you the opcodes here, the opcode table. So yes, like I said, we're getting a bit more technical here. So each opcode is a byte. And if you have if you looked at assembly code before, you kind of recognize a lot of this stuff. You have the arithmetic operations to add and subtract. All this, like we said, they operate on the stack. To add values together, you have to push them on the stack, and you get the value back on the stack. You have a lot of opcodes to just load and store memory. And as you can see, WebAssembly only uses some fundamental types: 32-bit or 64-bit floats, or 64-bit, 32-bit integers, and nothing else. That's all it deals with. And then you have these opcodes for dealing with blocks and loops. And yes, what I mentioned about the interesting thing about control flow is that there's no go-to statement. You cannot jump to specific locations. The only thing you can do is you can jump to the end of a block, or you could jump to the beginning of a loop, and nothing else, which makes the code is kind of easy to verify that it doesn't do anything really stupid, and also I guess it's easy to generate actual code to execute from it. Okay, let's look at some code in Compiler Explorer. Compiler Explorer has a WebAssembly target. So this is the simplest function from the examples. Multiply two numbers together, and this is pretty simple. So locals, local number 0 is the first argument of the function, etc. So the first locals are always the arguments. So very easy. You put the first argument on the stack twice, multiply them together, and then you end the function because the return value is on the stack. And if we take the example where it actually sums all the elements of an array. Now we can look a bit at the control flow I was talking about. So yeah, these are a bit more code, but it's not that weird. Put a constant on the stack and set the local variable number 2, which is the sum. So you clear the sum. Here you start a block, and here the block ends over here. So this code actually just checks if the sum is 0 and skips all the way here. And this is the loop. And something you can notice here that there are a lot more opcodes on this side than on the corresponding x86 side here. And this all comes from this stack-based approach again. You can't just sort of, if you want to increment the local variable, you need to first put it on the stack, put the 1 on the stack, add them together, and put them back in the local. Yeah. So this is not, it takes a lot more opcodes. And another thing that I should say about these constants here is that constants in WebAssembly are variable length encoded. So these actually, in this case, they're small, so they take 1 byte. But if the top bit is set, then it will be extended to the next byte and so on, kind of like UTF-8. So you have to deal with that when you're decoding WebAssembly. And if you put this together, this is one big problem, I think, with WebAssembly that sort of we've been hit by as well, is that the format, the instruction format here is not at all ideal for actually executing as it is. So that's why all, if not most runtimes at least, need to pre-process in some way to get it to run fast. And then, so I mean, it's designed to be very small and compact to be loadable over the network, but it complicates things a lot when you have to pre-process it. And in our case, it just takes a lot more RAM than we want it to do. And all the runtimes do this differently, so there's no standard way of doing it. So we would like to be able to maybe do it as an offline process, maybe, so you can have a faster format in flash memory or something, but it's not. So we do what I think most embedded projects do. I don't think there are that many, but we actually just compile this ahead of time to native code. It's like the only way to get the benefits that we need. Otherwise, it just will take too much RAM or be too slow. And I think if I could be, it would have been better if they had this kind of format that was actually pretty fast to execute and then just relied on some kind of simple compression if the size would have been a problem. But that's where we're at. Okay, let's go back to the slides. This talk is going faster than I
have a question.
Yeah.
When you say local dot, does the function have its own stack in addition to sort of the...
there's no stack. Local. There's just a bunch of locals. There's a stack for the operation stack, but locals are just every function defines all its locals, how many locals it has. So in the function segment, you define all the functions, the prototypes. So how many arguments they have, which defines how many locals are reserved for arguments, and then how many locals it reserves for the rest of the function. So the locals are just, yeah.
So there were specific opcodes for call and return, right? So that jumping to a new function doesn't touch the regular stack. Is that correct? Like the locals don't live in the stack. They live on a separate stack.
Yeah. It's not even a stack, I think, but sometimes usually you have something called a shadow stack for doing things that are required by C++ when you put large structs on the stack, and if you do things that actually need the stack, then you have a separate stack for that. But locals are locals, and the stack is just for, I mean, still the stack is there's one stack, so if you jump to another function, everything on the stack is preserved. And the return arguments are on the stack, I think, but I'm not sure now that I mention it. I said that the return arguments, I think, are on the stack and not in the register, in the local, even though arguments are in locals. Yeah. This was just how the variable length encoding worked. This is actually not you can't really write super efficient code to decode this, so that's also, UTF-8 is better, but at least you know up front how many bytes. You can look at the first byte and you can see how many bytes will be used, but in this case you can't. You have to read each byte until the top bit is 0, then you know you're done. And when we talked about this is two very common constructs that you will see if you look at WebAssembly. You have the block and the loop, and this BRIF0 is like extremely common because in the block case it just means jump to the end of the block if not 0, I think, and the same for loop, jump to the loop if not 0. So if you have a loop with a counter, you're going to see this, and if you have something that want to skip something because of a condition, you're going to see this. The only time those numbers get higher is if you're in a nested loop and you need to jump higher out. But I think I imagine at least that it's relatively easy to generate code from this format, but you have to do it for it to.
Yes.
Yeah, that's what I was mentioning. Okay, so a little bit about the memory model. Like I said before, it's all based on that you actually have a large linear memory that you can access. And there's like an opcode that's called memory grow. So if you need more memory, you're supposed to just have it directly. And if you have a desktop or something where you can use mmap, then that can be fine because you can make sure that everything becomes nice and linear. But for us, again, on embedded, that doesn't work. So what happens if we call memory grow? It just allocates a larger array and frees the old one every time. This all takes place in pages of 64K. So if we don't allocate any memory up front, and we just sort of rely on this growth to work, you're going to see an access pattern like this. Okay, we have one block called A, and now we need that to grow to 2. So we free, lowercase a, now that's the previous free block, and B is now the new memory. So we have one empty block of wasted space at the beginning of our linear memory. And now we grow to 3, we still can't fit it. So we have 3 empty blocks and 3 used blocks, and still, then we grow to 4. Now we have a lot of wasted space, and not until we allocate our 5th block can we reuse the old freed blocks. And this you kind of waste half your memory if you rely on this to happen. So in our case, we just say that you have to allocate everything up front, and it's a critical error if you need to grow the memory because we can't afford that, wasting that memory. That's also another problem with WebAssembly and embedded. Okay, any other questions so far?
Is it like Java bytecode? Does it have any like type saved? So you don't restore.
Yes. No, I think you're allowed. I'm not sure about aliasing.
Depends on the runtime if it's safe or not.
Usually, it's just memory, so you're allowed to load and store memory. There are no objects. It's just floats or ints, and then you can do whatever you want. I'm not sure if it's incorrect to store a float and load an int from the same location.
That's correct. That's incorrect, yeah.
No. Okay, I have some. Yeah.
Another question. How similar is this to JavaScript? Like, is there just a number type, or do you have types like floats and ints that you're talking about?
That's kind of the Java. That's where you saw that in the example JavaScript code, they had this common pattern that you see that they OR with 0 to force it to become integers instead of their number types. So it can actually.
But there's only in the JavaScript spec or whatever. There's only one type. It's a number.
Yeah, but it becomes an integer temporarily when you do so those things.
The binary operators are say that it has produced 30.
But as soon as you store it somewhere, it's a number again.
But as far as types on the stack is concerned, they're all numbers.
No, there's floats or ints. Again, I think it's going to be an error if you push a float and try to pop an int, but it's still. Okay, I have one extra section and then one bonus section, which seems like we're going to have time to get to. So I'm going to talk a bit about threads. So threads used to be not doable with Wasm.js and initial versions of WebAssembly, mostly because there was this thing called there is a thing called web workers, which has been around since 2009, which allow you to run things in parallel on the web, but you cannot share. Well, you couldn't share data between web workers. You can only start it, and then when it was done, you could read the result. And you can't use that to implement like pthreads. But then in 2017, something called shared array buffer was introduced. So you could actually have a buffer that many web workers could access simultaneously. But then something happened just like half a year later that made them turn it off again. Who knows what happened? Jonas knows?
Meltdown.
Actually, Spectre, I think. Because
Spectre is a general name. A meltdown is a specific case of it.
Okay. But basically, there was a way to read memory from other threads by using timing attacks. So you could sort of, with some tricks, you could sort of see if things were in the cache or not, and that way figure out the contents of memory that was not in your thread. And one of the things that you needed was a very accurate timer. And first they fixed it so that like get time or get date was not as accurate as needed, but what you still could do is just start another thread with a shared array buffer and then just increment a value there as fast as you could. And then you could read it from another web worker and you had a pretty high-res timer. So they had to turn it off just because of that attack. So I actually, when I started now with WebAssembly, I thought that you still couldn't use threads. I thought it was, but it turned out that like a few years ago, they actually reintroduced it by using something called cross-origin isolation, which is basically you claim in the headers of your the web service says like, oh, this page will only load data from its own. Like it limits what you can put in image tags and has to just your path and nothing else. So it knows that if you use WebAssembly 2 modules, you can still use this attack, but you can only attack your own code and not anyone else's.
Say they turn it off, you're talking about the browsers?
Yeah.
You're talking about the embedded Runtime.
No, this was on the web, yes. Both Firefox and Chrome and Edge turned it off for a few years. From like 2018 to 2021, it was off. Now it's on again. So you can have nice things. Yeah, those are the headers. Okay, so then we get to this little. Now we can actually see some C++ code. So this is actually it's related to WebAssembly in the sense that this is some things that came up when we started using WAMR and exposing functions from native code to WebAssembly. But the actual problem I want to talk about has nothing to do with WebAssembly, but it's a good example. So when we run WebAssembly in this runtime, if you want to be able to call functions that are defined in C, you need to define them and make them available to the WebAssembly. And the way to do that, and this is directly from the documentation, is that you define these native symbols. And it's like you have to find the name, a function pointer, and a prototype. So as you can see, we have some examples here. The function pointer is just a void pointer, and the prototype is just a string. And all the functions that you call, they need to have that prototype, that execution environment as the first argument. And then you can list as many of these as you want. And I mean, thing that I sort of thought directly when I saw this, what if you make a mistake here? What if you miss one integer, if you forget that execution environment type in the first, like, there's not going to be any compilation errors at all, and you might not even notice it when you run it. So it's pretty brittle, right? And we were actually looking to implement something, a UI library called LVGL, and it has like hundreds of functions that we needed to expose. And also, those functions don't have that prototype, and they deal with pointers, which WebAssembly doesn't do, and they want UTF-8 strings, and our assembly script code use UTF-16. So if you just take like one example function, like set the text of a label, this is kind of what you would have to do for just one of these hundreds of functions. Like you needed to do some way to convert between integers and pointers through some lookup table. We need to decode UTF-16, and we need to make sure we feed that the code again, and just make, and everything has to just be correct. And like the idea of doing this for like 100 different functions was just not, feasible. So of course, if you use C++, you can do magic. You can actually deduce types of functions at compile time. And with some template meta programming magic, we could instead do something like this. And this is what we did. You have a template argument, and you extract all the type info from that, and you can generate all this code at compile time. But of course, this is a bit complex. And I'm not really, there are a lot better C++ programmers than me. But there are also a lot more programs that don't know that at all. So this is like a subset of that code. And like if you, how many here thinks this looks like just gibberish? Quite a few. And how many thinks that I think I can do this a bit better? I think some of you will say that, because this is not ideal. There's like two indirections here to figure out things. I'm calling with a null pointer there. I'm not an expert at these things either. But still, this sort of, there's some, I don't think I will even go into sort of what happens, but you can, you sort of extract all the types, and you can generate what you need. And you can also do, like, if this is a pointer, it needs to be looked up in this table. If this is a string, we can do in UTF-16 decode, etc. But so the problem is here now, if you work at a project or at a company where there are no C++ programs at all, this is completely unmaintainable. So what do? Do you claim like this is the only way to do this, so we're just going to have to live with it, and if I'm not there anymore, this is just going to fall apart? Or do we say, we just have to do it by hand because we need maintainable code? And that's I think it's it.
You put it in the libraries and say it's okay.
You just don't tell anybody that's there. I mean, generation, actually, we have now, in this example, we actually can probably solve this, because it turns out there's LVGL has provided a way to generate a JSON file describing their entire API. So we can use that to generate all this C code instead. And I think that's probably what we should do, because, then they're probably just going to maintain that large chunk of C code, but at least they have something to begin with. But it's, I don't know, it's a balance between maintainability and function, I guess. Yeah. And I think that's actually it for me. Any more questions before we? Yeah.
What are the advantages of WebAssembly that you get for management?
That's a good question. I didn't read it. You mentioned why would you ever use this on an embedded platform? Yeah, it's mostly the sandboxing aspect, of course. I mean, you really don't want these things to crash when it's running on an appliance that you cannot update, and it takes like a year to deploy. So and since traditionally all this has been written in C, it's not uncommon for things to crash. So that's why it's been a popular way. Now you can also take C code and just compile it to WebAssembly, and it becomes safer. Actually, there's tools for just doing exactly, just take the C code, compile it to WebAssembly, then convert it back to C, and just link it put it in as normal. And you have to, of course, since you can't access memory the same way, you need to do some magic, but still, then you can sort of just box C code that way and make it safer but with the penalties that comes with it. But that's, yeah.
Do you have a feel for the performance overhead compared to just running C?
So in our case, on the embedded runtime, which is not the fastest one, I think we're using ahead of time, and then we're at like 2x slowdown, which is like the original. I think that like the fast runtimes on desktop, they're claiming like they're within like a few % of native speed, but they do a lot of magic to get to those numbers.
What kind of embedded device do you want?
What kind of
Embedded device?
embedded device? In this case, it's going to be like washing machines and ovens and stuff.
So what kind of safety improvements do you expect or do you want from using WebAssembly?
Well, the basic thing is, of course, just bounce checking everywhere and null pointers safety. This, like you're not going to crash. The runtime will throw or just tell you that things went badly, but it won't crash. At least, I mean, I'm pretty sure there are bugs in the runtimes, but the way it's supposed to work is.
Did you consider other safer languages or languages with bounce checking?
Yes, we started investigating Rust, so Rust and WebAssembly is also an interesting combination because Rust in itself is a lot safer. So the WebAssembly, I don't know how much benefit it gives you. Do you? No. So, but again, Rust is a hard language. So, and also we were using this real-time operating system that was pretty incompatible with Rust. So we put that on the shelf, at least for now.
Have you considered running UBSAM embedded instead of going through WebAssembly?
Well, then you need to cover all your use cases.
Fine. Do it.